All right, so building upon the last video, we ran a basic simulation. So this was an SCDS column in which we had a feed of methanol and water, so it's 55% water. And we sent it to distillation column with 12 stages. So that 12 stages, right, includes the total condenser and the partial reboiler, so 10 trays plus a total condenser and partial reboiler. So we played around with this, right, and that was great. Um, but what we want to look at is the next problem, problem 4, mentions shortcut distillation. And so where shortcut distillation is going to come in is with the SCDS column is where rigorously solving our column problem. So CHEMCAD's doing a tray by tray mass, energy, and phase equilibria. So mass and energy balance and solving our phase equilibria expressions tray by tray for that entire column. And so that could be, computational cost or computationally difficult depending on the system. But then also, there are some parameters. We need to specify things like um, boil up, maybe a boil up ratio, reflux ratio. Maybe you're specifying duties of your condenser and reboiler, our feed stages, number of stages. Right? There's a lot of design variables to take into account when I'm first trying to come up with some initial basic design of that column that I could then optimize. And so that's where a shortcut column could come in handy. And so what I'm going to do is I'm going to delete this column, okay, and then I'm going to scroll down and I'm going to find a shortcut. All right, shortcut distillation. So I'm going to drag in shortcut, okay, and shortcut's just going to have a single input, so it's going to be basic, and a single output. Let's see if I can connect it. Single output. Okay, cool. So my initial inlet stream, it's still defined the same. Now when I go to my column, I have a single inlet, and when I use the shortcut, this is going to be valid for non-azeotropic systems. Okay, so we've got we're assuming we're applying this to non-azeotropic systems, and so there's going to be modes, right? And so the first one's rating, Fenske, Underwood, Gilliland, and then design, Fenske, feed tray location, and then this Kirkbride feed tray location. Okay, and so we'll kind of look at all of them. But if I start with this Fenske, Underwood, Gilliland, so it's a correlative-based method. So we'll keep, we'll say we have a total condenser. Okay, you have total or partial, no partial with decant. Remember, no minimum boiling azeotropic systems. Okay, so in terms of rating, okay, let's see what it tells us. I'm going to specify a number of stages. I'm going to say I have 12 stages, and we had a reflux ratio of 1.25. I'm specifying the green items. Light key, okay, my light key is methanol. Okay, and my heavy key, well, that's water. Okay, so if I have more than one component or more than two components, right, I could still specify the two key components of interest. My light key, the most volatile, and heavy key, the least volatile. And I'm going to specify that. I don't need to specify anything else. Okay, so I'm going to click OK. Yeah, I thought I didn't have to specify it. It wasn't green, but let me. Yeah, they want a heavy key split, but not. I can't specify light key split. So let me try a heavy key split, and let me just do 0.01, and let's see what happens. Okay, if run selected, it runs. Okay, and so what I have is coming out the bottom, right? I get a stream which is 99% water. Right? I think that's where that heavy key split is. And then coming out the top, right? Essentially, it's 54.45% methanol, and that is right. When in 55 mole percent ethanol. Oh, that's because it's not a mole percent, right? And then it's 99.18 mole percent methanol coming out the top. Cool. Um, so yeah, so specified a heavy key split of 0.01, and so again 0.01. So I've got to go get my kids soon. 0.01. So the coming out the bottom. So let me put it in terms of mole fracs, right? It's essentially it's 0.99 is my mole frac of water, right? So 0.99, 99%, right? And so it's pretty close, 98.8%. Cool. In order to do that, right, now it's filling in some details. So we said we had 12 stages, a reflux ratio of 1.25. So it calculates the condenser and reboiler duty, the minimum stages, and then the optimal feed stage would be stage 6.536, which is about where we were last time when we varied the feed tray location, just in that rigorous SCDS column. Okay. In terms of other, so okay, what do we get out of all of this? Well, by specifying the number of stages and the reflux ratio, and then our desired split. Okay, so 0.99, so 99% of the methanol we want coming out the top. So this is what it computes as those required duties for our condenser and reboiler. Okay. Cool. Oh, in terms of other modes of operation, so in terms of design, so to design, so now I'm going to delete the reflux ratio number stages, right? They're not colored. So I'm just going to say I have a total condenser, and then I'm going to specify methanol and water, and I can specify my light key and heavy key split. Okay. So let me come back in. It says R divided by. Okay, so let's do R divided by R min. Okay, rule of thumb of say 1.25. Okay, if I run that. Okay, so with an R divided by R min of 1.25. Okay, R being my minimum reflux ratio. That requires 17.6 stages. There's my condenser and reboiler duty. Okay, and again, right, I'm going to get my same split, 98.8% methanol coming out the bottom. Okay, or water coming out the bottom, 99.2% methanol coming out the top. Right, all is good. Right, 99% of my methanol going in is coming out the top. Right, cool. But yeah, so so what did I specify again? Okay, I specified the value of, and so let me try something. If I just were to specify a number of stages 12, okay, no, it doesn't work. You need to specify R or R over R min, right? So my reflux ratio is like what we're given in the problem, 1.25. Okay. And so if you specify a value of 1.25, right, it tells you the number of stages. So the reflux ratio of 1.25, optimal number of stages is 12. Okay, cool. Okay. Where the R divided by R min is, there's rules of thumb for computing your reflux ratio with respect to the minimum reflux ratio. And so I want to say the rule of thumb from Giancopoulos is around 1.2 to 1.25. Okay, and that's where I went in and I specified R divided by R min instead of my reflux ratio. And so now if I kind of put this together is okay, so now if I have this separation, this is the split I want to achieve. Well, from this design, with a reflux ratio of 1.25, I would get about 12 stages. Okay, or if I used R divided by R min as a rule of thumb, I could get that as well. Then let's see, once I have that, if I went back to rating, okay, then clicked OK, then it actually gives me an estimate of the optimal feed location as well, right, which is the 6.536, because I didn't get that here, right? So if I go back to this one, all right, take it back. So with my design, right, it gives you the optimal feed stage along with the number of stages for that reflux ratio and that split. Okay, and so again, where this could come in handy is if I'm trying to design a column for a given process, this could give me a starting point to then optimize my column around. Okay, and so that's all I wanted to mention in terms of shortcut. In terms of R divided by R min, I thought I had my Giancopoulos book here. This is the design book, right? But they're going to have heuristics and rules of thumb in there to get you started as an initial starting point in terms of designing a column. Okay, and so then once you had an initial estimate, you could delete this, bring in your SCDS column, and perform a more rigorous calculation. Okay? But hope that helps. We'll see you shortly in class.